Clinker Factor, the cement industry podcast.
Welcome to the Clinker Factor, a podcast from WCA which looks at the cement industry's response to climate change around the world. I'm Ian Riley, CEO of WCA and your host on the Clinker Factor podcast. Today I'm talking again to Matthias Mersman, CTO of KHD, and this is the third of our series on the application of technology to reduce emissions and the impact that we have on the environment. And today we're going to talk about alternative fuels. So Matthias, to start with, how should we categorize alternative fuels and how should we break down this whole subject?
Yeah, Ian, you're putting the most important question at the beginning. That's a good start. That is the million-dollar question, I would say, because we have to understand basically one thing when we talk about waste-derived fuels. No matter what category we pick, all of those materials have one thing in common, and which is none of these materials has been manufactured or put in circulation into our lives with the intention to being burned. So we are using all of these material far away from what they have ever intended to be manufactured for. So that's making it very hard to categorize. The usual term of differentiation, however, is that we mostly categorize into industrial waste, commercial waste, and municipal waste. And then depending on the way it is prepared, processed, and utilized, there is a number of different names to be put to it, most of them consisting of three-letter acronyms. So it's a very variable name tagging on these materials.
So before we go any further, let's just touch on biomass. So obviously that's separate from a waste-derived fuel, but it also has the same problems in the sense that it wasn't a designed fuel. So when we're talking about alternative fuels, do you include biomass or do you think of that separately?
Absolutely. Biomass is a differentiation in its term that refers to its say chemical, biological source. But it can also be a commercial waste from a commercial biological farm or whatever. So in that sense, it also is a commercial waste. It can also be part of municipal waste. Municipal waste contains also some biomass. And even if you have, for example, industrial plantages, for instance, in other parts of the world, it can also come from industrial activities. So it would also be industrial waste. It refers to a different category.
Right. And I suppose we do sometimes have, although this is not the usual situation, but we do sometimes have material, generally wood or bamboo, that is specifically grown to be burned. So I guess that's a slightly different category from the others where we're looking at a byproduct.
That is true, Ian. I didn't have that on my radar when I started explaining. I absolutely agree. These are then not waste-derived fuels, but these are really biogenetic fuels.
Right. Okay. Well, let's deal with the waste-derived fuels, and maybe we'll return to other fuels later. Maybe the most interesting part, of course, from a cement producer's standpoint, is the fuels that have a higher heat value. So a lot of the industrial wastes that were dealt with by the industry early on were things like paint sludges and oil spills and things like this that had pretty attractive heat values. So in those kind of wastes, is the key challenge the handling of them as opposed to the burning?
Again, this opens a wide field of possible answers. The attractiveness, of course, is depending on the best possible achievable benefit to low cost ratio. And usually what has the highest calorific value and the most easy properties for handling is very soon identified by the supplier as valuable. So the price will go up immediately, and which reduces the attractiveness for the cement plant at once. So it's a combination of how much effort you spend on pre-processing and how much you spend on co-processing. So the conjunction of those two in an individual case must be optimized.
So in Germany, you have probably one of the highest usage rates, one of the highest thermal substitution ratios of anywhere. Do you want to take us through a little bit how that developed in Germany, and which fuels were used first, and how that's progressed over the years?
Yeah, that's actually interesting because it tells a story, and it serves as a pattern also for other regions which are coming up, because it is based on a natural sequence of activities and choices and decisions being made. So in Germany, actually, really the average TSR, thermal substitution rate, is ranging short below 70% already. So Germany has a long tradition in it, and by wrapping up this chronology, we can really learn something about what are the drivers and what is meaningful to do in what phase of the game. So back in the 1950s in Germany, the cement plants started burning tires, car tires. And that's has been a very smart move, because car tires contain a lot of heat. They are easily handleable. They are particles which you can store on a pile. They don't get sticky if the rain comes on it. So they contain a lot of good advantages. And in the beginning, of course, they also got good gate fees for it, for disposing them off. Later on, the interest of the cement industry was increasing because they found they could save a lot of fuel costs with it. So they started looking for additional ways to substitute their fossil fuels. And then, of course, the first thing you do is you actually look after material that is waste and that contains a lot of heat, and somebody has to dispose of. And naturally, you come to solvents, color residues, and these kind of things, which you can also handle quite easily by injecting it into the burner pipe. Now you reach some certain TSR rate with it, and you find out, for chemical reasons, for example, containing too much chloride or other components which you don't want to have in the cement process, you need to find different material, still different material, but now your appetite has been cured for a little bit. You are maybe at 30% substitution rate, and you still want to increase because you are in tight competition under immense cost pressure. So you're looking for new alternative fuels. And then the race is really on since the 1990s, I would say, in Germany, where people started using municipal waste and learned their first lessons on how much they have to be pre-processed in order to be co-processed correctly. And then the plant equipment was taken into the considerations for adaptation and improvement, like special types of calciners. So the effort was then shifting to the co-processing adaptation rather than the pre-processing adaptation.
So before we go on, could you just explain in Germany what the municipal waste contained? For example, in China, where I was working for many years, we had a lot of organics in there, and the municipalities were looking for us to treat the whole waste stream, not just the parts that we wanted.
Well, in Germany, I would say the municipal waste was still containing a lot of high quality components, high quality in terms of what you want to have if you want to use it as a fuel, which means a lot of plastics, not much glass or inert material, because there was a system in place that separated different fractions of waste from the households. And it was quite easy to pre-process the municipal waste into a high calorific, high quality RDF fraction without much glass or stones in it. Now, the interesting thing about RDF is it is different not only in every state, it's also different every day of the week, and it's different in every region of the world. If you take, for example, India, there are a lot of pickers on the dump fields. They pick out, say, rubber parts and other parts they could sell on the regional markets, on the local markets. So the mixture of materials is a completely different one, which is, for my understanding, one of the major reasons why, for example, today in India, the substitution rate has not yet reached levels which you would expect given the maturity and the technical excellence that the Indian cement industry has.
Yes, I think it's noticeable both in India and in China that if you look at fuel efficiency and other technical parameters, both countries are extremely good. But on TSR, it's still low single figures.
Yeah, that's true. That's striking. And I'm sure this has to do with the environment of waste-derived fuel utilization. And that's another critical aspect in this game. There might be a cement plant ready to receive and also pre-process material and then co-process it. However, if there's no collection system in place, if there's no, say, political environment, social-political environment that is supporting the collection of waste, but dumping it just everywhere so that collection cannot be done efficiently, then this material is simply not available. So we recognize that if we follow through the development of secondary fuel usage in the world, you see that this is behaving like a wave that is propagating forward as the economies develop into a critical state on a threshold kind of development where dumping material is organized from state. And the next step then is that dumping is getting expensive. So that is something that kicked in, for example, if you looked at that in Germany, the development, or in Great Britain as well. So that is really then driving the utilization of waste-derived fuels.
Yeah, absolutely. So coming back to the German story and the MSW, was the organic, the kitchen waste, was that being composted or was that in the MSW?
That also depended very much those days on the region in Germany. Germans are being famous for spending much motivation on separating waste. So we had organics being separated on private motivation by many households. So Germany was quite advanced in separating waste with a view on utilizing this. Of course, this was also not perfect, and due to, say, lack of a very stringent organization all the way down through the value chain in all regions of Germany, there were some regions where households had separated all this waste and then found their waste to be mixed together on the dump site again. So nothing is really ideal, nothing is really perfect, but that is something we have to get accustomed to and we have to accept when we talk about waste and waste-derived fuels.
Yes, I think we still have the same thing happening in the UK at the moment. But anyway, this is only in some parts of the country. Other parts of the country, as you were saying in Germany, also are much better at separating these wastes.
What it tells us is that thinking about waste and waste utilization is something that you need to think all along the value chain. I'm just already talking about the value chain because this is actually today valuable. And that's the magic thing about it. It starts as waste and it turns into a valuable. And if you want to ride this horse. You'll have to organize it all the way down to the value chain. It doesn't make any sense for a cement plant to try and use RDF if the socio-economic system in its environment doesn't supply it.
Yes, absolutely. So let's just continue with the development in Germany. So you got up to MSW. What happened after that?
Yeah, then the real active, from the technological point of view, the real active era, I guess, started in the late 1990s, when cement plants, first cement, started reaching TSR rates beyond 50%. Then actually this stream, which we know under RDF or SRF terminology, became very, very much famous, and everybody wanted to have it. So that has an impact on its pricing as well. But it represented a form of waste-derived fuel that was rather easily handleable, close to being standardized, because it could be used in calciner and also to some extent in the kiln burner. So the two firing locations in a cement process could well be served with it. However, this asked for tremendous improvement in the pre-processing and also in the co-processing technology. So in order to fabricate, to manufacture a good RDF, specialized companies intensified their technological setup and also their business models in order to produce better RDF, came up and developed. And at the same time, as the RDF got more and more expensive, people developed some interest in saving money by trying to use the coarser, lower qualities. But if you do not spend that much effort in the pre-processing, at some point you'll have to spend it in the co-processing. So this means at the same time, the co-processing technology, calciner technology, burner technology was ramping up. That was the time when the combustion chambers have been introduced, which introduced an open flame combustion concept in the calciner that was previously not wanted, because open flame means high NOx. And we had just finished the low NOx calciner era, avoiding high temperatures, avoiding open flame. Now we wanted to spark ignition with the big size, lumpy particles of the RDF, of the low quality RDF. So we needed an open flame to initiate the combustion. So that is when the combustion chambers came in. As the decades went by, the urge for ever low-cost RDF kicked in, and that produced a series of inventions connected to the co-combustion, co-processing, the combustion technology in a cement plant, up to the level what we're having today. We're having almost any of the big OEM suppliers, they do have some specialized reactor in their product portfolio, which allows really to maximize the feeding of big particle secondary fuels. Like we in KHD also have this pyrorotor, which is a rotary kiln concept, which is a very rigid and robust type of device that allows to put in big size and big mass flow of secondary fuel.
So with today's technology, you're not getting high NOx out of the calciner, right? That's been controlled.
Here is something that helps us in the cement industry. Even though the design of the calciner is not really low NOx anymore, due to the fact that most of the secondary fuels contain at least one portion in the mix that is showing a high degree of volatile matter, like the plastics fraction, for example. And this fraction sets free during its pyrolysis, which is the first step of the combustion. They set free a huge amount of carbohydrates. And these carbohydrates are the most effective NOx reducing agent that is available. So if you do it right and you put the secondary fuels at the right position in the calciner, giving them the right regime in terms of temperature and oxygen for them to set free their carbohydrates, then this NOx reduction step is much more efficient even than the most efficient low NOx calciner was in the early days. So it's no problem if you do it right to achieve very low NOx values when using secondary fuel.
Yeah, no, this is exactly what I've seen in the operations that I've been involved with. So if we look at the challenges that companies face, so perhaps learning from not only Germany, but other places in Europe that have increased up to this high level of TSR, and thinking about companies that are operating in developing countries where the regulation system is not yet mature, and so they're still relatively early on that ramp up. If we look at the technical challenges that companies will face in trying to increase from their current low levels up to the same sort of levels we're now seeing in Europe, what are the things that you would put at the top of the list as being key issues to focus on?
Yeah, the most important thing is, if you want to ramp up your RDF, is to be open to learn from those people who have done it. I very much intentionally stress that before I come to the technical point, because the thrill to save money by replacing fossil fuels with waste-derived fuels is so strong that the experience says that most of the projects have been run by wish rather than by reality. And I think there is no single cement plant that can say that their TSR raising projects all went by push bottom. It's not easy switching to high degrees of TSR. You'll have to devote yourself to it. You'll have to be prepared to very diligently discuss what your options are and to very diligently design your co-processing and pre-processing in a way that satisfies the requirements of the process in the end. Because you can buy MSW or RDF or SRF. You can handle it. The moment you put it into your kiln plant tells you whether you did it right or wrong. And if you did not do it right, you will have coating, you will have clogging, you will have massive problems in operational stability. You might have production decrease. And there are plants which did not like their first steps in TSR at all, because there are lots of shutdown and cleaning. So it's a complicated matter, because these secondary fuel particles, as I said, they have not been manufactured to act as fuel. Sometimes they are nasty.
So the first thing to do then is to look at the pre-processing, if you like, the preparation of the fuel, and make sure that you've done enough. I guess you've got to worry about moisture content. You've got to worry about the consistency of the fuel, and specific contaminants in the fuel that might cause you problems. Is that right?
Absolutely, absolutely. In the end, if you look at it from the technical point of view, these particles which you put in there, they do have a chemical and a physical property. First of all, of course, the chemical properties need to accommodate the requirements of the process. Talking about chlorides, for example, and other components which are harmful for the cement process. Even if you can burn them, ideally, just by putting them in, they might destroy your quality. So you'll have to look after the recipe. You might also have to adapt your raw material mixture in order to get to the right clinker quality in the end. So that is the chemical part. The physical part is much more complicated. That is talking about moisture content, that is talking about particle size, that is talking about even shape these particles, like their pneumatic behavior. If you have too many high-density three-dimensional particles, they drop down into the kiln inlet chamber while you want to have them in the calciner. So that is completely shifting the location of energy release into an area of the kiln plant where you don't want to have it. So there's a lot of things to be looked at. And you were putting the question whether you would first want to look after your pre-processing. I would say pre-processing and co-processing, they have an interface. So they shake hands at a certain position. And that certain position is that the pre-processing is delivering that material in an appropriate pre-processing state that is appropriate for the co-processing technology that is used afterwards. For example, if we think about this pyrorotor, which I just described, that is the device, the technical device that can take the biggest particles, then you don't need that much pre-processing. But if you want to use MSW, for example, RDF or SRF in the kiln burner, then you have only a limited retention time for that particle to burn out. So you need a very high pre-processing depth to use that. So it's an individual case that's making it complicated.
So are you seeing overall a trend to burning in the calciner as opposed to the burner?
Yeah, also that is interesting. If you see if you arrange the steps for increasing TSR along the cement production line, clinker production line, then the first step is very easy to put, for example, tires in the back end of the kiln. That gets you to some 8%, maximum 10% substitution. Next step would be, as you may have no specialized calciner, next step would be that you substitute maybe 20, 30% of your main burner fuel by secondary fuel. That gets you to something like 40%. If you want to increase more, you cannot do that in the kiln burner. Because this is the place where the clinker quality is determined. So you better take your hands off that for the moment and then look at the calciner, because the calciner is where 60% of the total heat input is done, and the combustion environment allows lazy combustion, which you cannot afford in the sintering zone. So the next step would then be in the calciner. So you need maybe special injection technology for the calciner. You might want to change your meal injection ports. You might have to install a bypass, because then you would be reaching chlorine inputs, which would be harmful. So then you ramp up everything in the calciner until finally you can go to up to, we have plants running with 98% calciner substitution rate. So that gets you to, say, 80% of total substitution. And what's remaining is the last bit of high quality fuel you need for the sintering zone in order to control quality. And if you want to go to beyond that, and there are plants that are running something like 90, 95%, then it's really the high art of process management.
And does the latest process technology, the Industry 4.0 type of developments, does that help you with that process control?
Well, definitely. And that is the clear path forward. The increasing TSR, and specifically with biogenetic fuel, is one of the major pathways on any CO2 reduction agenda. And it's, by the way, the only of all those levers that are at the same time helping reducing cost instead of putting up new cost. So that is clear to be seen, and any percentage of substitution is welcome. And in the plants in Germany and in Austria, for example, we have arrived at a level of which you cannot proceed anymore if you do not pull all the registers you have. And that also includes modern type of online optimizer systems, model predictive control, digital twin, neural nets, everything you have.
So I think to summarize, we've got really two constraints, if you like, on the amount of TSR that a cement plant can use. On the one hand, we have the technical constraints, the sort of things that you've just talked about. And on the other hand, we have supply constraints. And in countries that have more developed regulatory environments for waste disposal, then usually there's more availability of waste. And as we talked about earlier, in many developing countries, there's a limited amount of waste that's available because of the collection system and the way that that is regulated. So I think one of the things that we see in India, for example, is that Indian companies are looking at biomass or the biogenetic fuels in order to make up that gap between what they are technically capable of and what they can actually source. So maybe we could just close by talking a little bit about these biogenetic fuels. Obviously we see wood chips used not only in the cement industry, but in the power industry as well. And increasingly, I think bamboo is being looked at because the growth rates per acre are much higher than they are for wood. What would be the other significant fuels that would fall into that category? Are there any others?
Yeah, I mean, of course, in India, for example, there's quite a tradition already also in using something like rice husks. But I'd like to make one remark with respect to wood and bamboo. The reason why we like placing a piece of wood in our fireplace, in our living room, is that we don't have to put new piece of wood into that fireplace before 2 hours, because it takes 2 hours for such chunk to be burned. Now, I did not find yet any place in the cement production process where I have 2 hours time to burn down a piece of wood. And that is a big misconception. Still too many people believe that wood would be an ideal fuel for a cement plant. It is only in terms of sawdust. All chunky wood is a real headache, and it takes so long to burn out that you will automatically create a problem in your system if you burn wood and also bamboo. If you don't manage to reduce the particle size to acceptable levels, and if you compare, for example, the ignitability and the burnout behavior of, say, a plastic piece, maybe 1-2 millimeter thick and edge length 20 by 20 millimeter, this thing that burns out within, I don't know, 3 seconds. A piece of wood that burns out in 3 seconds must be something like edge lengths 2 millimeter, 3 millimeter. So that is the magnitude of difference in individual burnout behavior of the different fractions in mixtures also of municipal solid waste. And that's very important to understand. So the biogenetic fuels, they are important because they contribute to the CO2 reduction. But using them in mostly they're also very humid, contains a lot of moisture. So that is really challenging to handle these kind of fuels.
Yes, exactly as you say. I think the pressure to reduce CO2 emissions is perhaps pushing companies to go faster than the regulatory environment in their countries, and hence the looking at bamboo and wood. But these fuels have their own issues of alternative fuels. Do you have any other suggestions that you'd like to put forward as sort of step one?
Carefully look at the pneumatic stability of your riser duct and your calciner. Then put edge length smaller than 30 millimeter into the calciner. Gradually grow and keep track of your mastering of the process. Of course, if you have a long-term perspective and you're decided to go that way, maybe you want to use biogenetic fuel strategically for your CO2 roadmap, then you should go for a reactor that is providing a long retention time. So I guess it's very hard to give general recommendations that are valid for everybody. You need a good master of process and certainly good advice.
Yeah, no, I think that's absolutely where people should start when they're trying to expand beyond what they've done before. Learning from people who've been there before is probably a very good starting point. So, Matthias, it's been a pleasure talking to you again today, and I thank you for taking the time. So we have one more chat scheduled, where we're going to talk about the plant of the future. So I look forward to doing that in a few weeks' time.
Thank you very much. Like always, it's a pleasure, and I'm looking forward for the next one.